Today we're going to explore the physical behaviors of solutions. In other words, how does a solution behave differently than if it were just pure solvent? And then we're going to talk about something that a lot of people have heard and a lot of people use this terminology, but not many people know what it really means, and that's electrolytes. But first we'll start out with some quizkins. This first question asks, what will be the solubility of nitrogen in water when the partial pressure of nitrogen is 800 torrs if the solubility of nitrogen is 0.0150 grams per liter when the pressure of nitrogen is 580 torr? Well, Henry's law tells us that solubility and pressure are directly proportional for gaseous solutes. And the two-point form that we saw is concentration under one condition over that pressure is equal to the concentration at the second pressure divided by that pressure. So what we're trying to find here is the second concentration, the concentration at the 800 torr. So let's fill in our numbers. First of all, 0.0150 grams per liter is the concentration at saturation, in other words, the solubility, when the pressure is 580 torrs. So we can set up the proportion on the other side, C2 over 800 torrs. Cross multiply and divide to get our answer here. C2 should have three significant figures in it because all of our data has three sig figs, and the answer is 0.207 grams per liter. This next question describes a solution that has 158.2 grams of potassium hydroxide in every liter. Its density is given, and then we have this situation where a lab technician wants to make some 0.250 molal KOH solution starting with 100 milliliters of this solution that we're describing here. And then the question is, what does she need to add to make this solution? In other words, is she going to have to dilute it with water, or is she going to have to add more KOH, and then how much? Stop the video and give yourself a chance to solve this problem. It's not real easy, but if you think deeply about what molal really means, you should be able to get at least part way through this problem before you get too stuck. I'll bring you an answer shortly and a solution. Well, here's the situation. In this liter of solution that's being described here, some of it is water. And I'm going to kind of denote that with this blue. But some of it is KOH. Now they're mixed together. They're not separate like I've drawn them here, but part of the solution can be thought of as the KOH, and part of the solution can be thought of as H2O. And we know something about that. We know that in this solution there are 158.2 grams of KOH for every liter of water. Other facts. We know the density, 1.13 grams for every milliliter. We know the molality that we want our solution to end up with. So this is a target number, 0.250 molal. That's what we're shooting for. And we know that we're starting with, initially, a volume of 100 milliliters of this solution. So the question is this: when the technician goes to make this solution, she's going to have in here some water. She's also going to have in there some KOH. What does she need to do to make this target 0.250 molal solution? Will she need to add a bunch of more water, or will she have to add some more KOH? And if so, how much? But we know what she's starting with is 100 milliliters. Well, I think that the first thing we should do is probably figure out what is the current molality of this solution, because if we can figure that out, then we should be able to determine at least if she has to dilute it or make it more concentrated. So let's figure that out first. Molality, remember, is number of moles of solute, I'm going to use U for solute, divided by the kilograms of solvent. So in this case, that means number of moles of KOH over kilograms of H2O. Let's find out how many moles of KOH are in there. We don't know much, but we do know the mass of KOH that's in there. It's 158.20 grams of KOH. The molar mass of potassium hydroxide is 56.105 grams per mole. And so that tells us that in a liter of solution we have 2.820 moles of KOH. Now if all we had to do is figure out the molarity, we'd be done. It's 2.820 molar. But that's not what we want. We have to know how many kilograms of water are there. If we knew the mass of the whole solution, we could figure out the mass of water because we already know the mass of KOH. So let's do that with density. We know that density is equal to mass divided by volume. So the mass of our solution should be the density times the volume. And the density is 1.13 grams per milliliter. And if we have a liter of this stuff, that's 1,000 milliliters. So the total mass of the solution is 1.13 times 1,000, which is just 1,130 grams. So the mass of water is the difference between that 1,130 grams and the part that we already know as KOH, which is 158.20 grams. When we subtract, we get 971.8 grams of water. In kilograms, that's 0.9718 kilograms of water. So now we're in a position to calculate our molality of our solution. Molality is 2.820 moles of KOH per 0.9718 kilograms of water. And that works out to 2.902 molal. Well, our target is 0.250, so we're going to have to dilute this a lot. So the first answer to our question is we have to add water. Now the second question is how much water do we have to add? Let's start working on that next. Thinking about the definition of molality again, it's number of moles of, in this case, KOH, that's the solute, divided by kilograms of water. And the number of moles of KOH is fixed. We're not adding any more KOH, so that's a number that's already determined. We have to work on kilograms of water. We have to know how many kilograms of water have to be added. Well, we have 100 milliliters of this solution, so let's first of all figure out how many moles of KOH really are in there. We know that there would be 2.820 moles of KOH in every liter of solution, or in every 1,000 milliliters. So in 100 milliliters, how many moles would be present? Well, it's 1/10 that amount. So 0.282 moles of KOH are in our 100 milliliter sample. How much water is in there now? Well, we could set up a similar proportion. We know that in the 1,000 milliliters, there were 0.9718 kilograms of water. So in 100 milliliters of the solution, there would be again 1/10 of that mass. So 0.09718 kilograms of water are present. How much water do we ultimately need is the next question then. Well, working with our definition of molality again and solving for kilograms of water is going to be equal to the number of moles of KOH divided by the molality. So that's 0.282 moles divided by our target molality of 0.250 molal. And this will come out to 1.13 kilograms. Well, some of that is already in there. In fact, we know we have 0.09718 kilograms of water. So we'll subtract that amount because it's already there and find out how much water we have to add. And the answer is 1.03 kilograms of water must be added to our solution. Next, we're going to investigate some things that are called colligative properties. And the word colligative actually comes from word parts that mean depending on number. So these are properties that depend on the number of particles of solute that are present, not necessarily what the particles are. We're assuming that the particles of solute are attractive to the particles of solvent, otherwise the solution would not have formed. And because of that, all liquid solutions of non-volatile, that means not easily evaporating solutes, like solids, have lower vapor pressures than their pure solvents. Why would that be? Well, if you think about it, in a puddle of water, you have water molecules attracted to other water molecules, and that's what keeps them from evaporating and creating this vapor pressure in the headspace up above. The strength of those intermolecular forces is what determines vapor pressure. High IMFs, low vapor pressure; low IMFs, higher vapor pressure. We learned that in the last series of videos. Now, let's say we throw in here another particle that the water is also attracted to. Like, let's say we have some HCl dissolved in here. Water is attracted to the HCl's in addition to the H2O's that are present. And so now that water molecule is attracted to more things, and it's less likely to vaporize, so that's going to mean fewer particles of gas in the headspace and a lower vapor pressure. This turns out to be a linear relationship, and the name of the relationship is called Raoult's law. The statement of Raoult's law is that the vapor pressure of solvent A, when it's in a solution, is equal to the mole fraction of that solvent times the vapor pressure of that solvent when it's in its pure state. So that little degree sign up there means when the solvent is pure solvent, what is its vapor pressure. So we can graph that out here on this set of axes. Along the bottom we've got mole fraction, and on the left side of the axis we've got pure A, so the mole fraction is 1. On the right hand side we have no A at all. So if we don't have any A, A is the solvent. If we don't have any solvent, obviously the vapor pressure would have to be 0. If we have pure A, then the vapor pressure would have to be the vapor pressure of pure A, PA naught, or degree sign. And since it's a linear relationship, we can see a straight line develop as we go from pure A to no A. So the lower the mole fraction of A, the lower the vapor pressure will be. In other words, the stronger the solution, the more concentrated the solution, the more solute is present, the lower the vapor pressure will be. That's Raoult's law. So here's a problem that we could work out with Raoult's law. Carbon tetrachloride has a vapor pressure of 100 torr at 23 degrees C. So that's the pure vapor pressure for CCl4. This solvent can dissolve C22H46, which is one of the components in candle wax. And that's non-volatile. It doesn't evaporate very readily, as you all know from observing candles. What would be the vapor pressure at 23 degrees C, so same temperature, of a solution of 10 grams of wax dissolved in 40 grams of carbon tetrachloride? So let's get into a bigger workspace and solve this problem. Well, Raoult's law says that the pressure of the carbon tetrachloride is going to be equal to the mole fraction of carbon tetrachloride times the vapor pressure of pure carbon tetrachloride, or PCCl4 naught. And we already know what this is. It's 100 torrs at 23 degrees C. So what we have to do to solve this problem is we have to figure out what's the mole fraction of carbon tetrachloride. Now, by definition, mole fraction of CCl4 is going to be equal to the number of moles of CCl4 divided by the total number of moles. Well, that's moles of CCl4 plus the number of moles of the other stuff, C22H46, the wax. So we'll have to calculate that from molar masses. It says we have 40 grams of carbon tetrachloride. The molar mass of carbon tetrachloride is 153.823 grams per mole. And so that gives us 0.260 moles of carbon tetrachloride. Dissolved in it is 10 grams of the wax, which is C22H46. This is going to have a very large molar mass. When you calculate it, it's 310 0.61 grams per mole. So we have only 0.0321 moles of the wax. So what's our mole fraction? It's 0.260 divided by 0.260 moles plus 0.0321 moles. And this works out to 0.890 for a mole fraction. Now remember, that's a unitless number. So now we'll plug this into Raoult's law and find out what the pressure of carbon tetrachloride will be in this solution. So it's 0.890, that's mole fraction, times the vapor pressure of the pure solvent, the pure carbon tetrachloride, which was 100 torr. And this works out to 89.0 torrs. So we can see the effect of Raoult's law here. When the solute is dissolved into the solvent, the vapor pressure is lowered. Now we just looked at Raoult's law for a solute that doesn't evaporate, so like a solid solute that's just going to stay put when you put it in solution. But you can occasionally dissolve a volatile solute in a volatile solvent. In that case, you have systems that obey Raoult's law. Both of them obey Raoult's law together. So this is a graph that allows us to see the effect of both of these things following Raoult's law. On the left axis, I've got vapor pressure for A. On the y-axis, I'm plotting the vapor pressure of B. And along the bottom, I've got mole fraction. Now, if I've got these two mixtures, if I have pure A, then the mixture would have to contain no B. And if I have pure B, then the mixture would have to contain no A. So at all points in between, I'm gradually decreasing my A and increasing my B concentration as I go across. So right in the middle here, it would be like 50% each, or mole fraction of 0.5. This would be 0.75 A and 0.25 B, and this would be 0.25 A and 0.75 B. So we're seeing two things changing at the same time. Well, we already know what's going to happen with A because we plotted that out. When it's pure A, the vapor pressure of A is vapor pressure of pure A. When it's no A at all, then that would have zero vapor pressure. So we can draw a straight line that connects these two. Now let's look at the vapor pressure of B. If we have pure B, in other words, the mole fraction of B is 1, then we're going to be at the vapor pressure of pure B. If we don't have any B, then it's going to be at 0. And again, we can draw a straight line to model what Raoult's law says. So what's the vapor pressure of the whole solution? Well, when it's pure A, the vapor pressure of the whole solution has to be pure A. When it's pure B, the vapor pressure of the solution has to be pure B. But in between, what is it? Well, let's take this point right here. I would have the vapor pressure of B, plus I'd have the vapor pressure of A, which is the same height. So if I connect the two together, if I add this height plus that height again, I would have the vapor pressure of the solution. Here I have more pressure of A and less pressure of B. Here I have more pressure of B, less pressure of A. It turns out that if you were to add all these up, what you'd do is you'd find a straight line that goes directly from partial pressure of A to the partial pressure of pure B. And this is the pressure of the solution. This is the actual pressure of A and B, the solution together. So here's the partial pressure of B. This is the partial pressure of A. And the red line that connects pure A to pure B is the partial pressure, is the pressure of the entire solution. So what does Raoult's law say then in mathematical terms? The total pressure, pressure A plus B, is equal to partial pressure of A plus the partial pressure of B. But we know the pressure of A is mole fraction of A times pure A's pressure, and we know that for B it's mole fraction of B times B's pure vapor pressure. And so that's Raoult's law for two volatile components in the same system. So here's an example. Acetone and water are both volatile components in the same solution. At 20 degrees C, acetone's vapor pressure, so this is pure acetone's vapor pressure, 162 torrs. At the same temperature, water's vapor pressure is 17.5 torrs. So what's the vapor pressure of a solution that's acetone and water, 50% each by mole? So that means the mole fraction of each of these things is 0.5. So Raoult's law is saying the pressure of the solution is going to be the pressure of acetone plus the pressure of water. But we know that that's equal to mole fraction of acetone times the pure vapor pressure of acetone plus mole fraction of water times water's vapor pressure as a pure substance. So we'll just plug numbers in here to get our pressure. Mole fraction of each is 0.5. Partial pressure of acetone is 162 torrs. And the partial pressure of water vapor is 17.5 torrs. When we sum this all up after doing the multiplication, we get 71.8 torrs, and that's the pressure of the whole solution. So the effect of dissolving water in acetone is to lower the vapor pressure of acetone. The next question is related to what we've just learned from Raoult's law, and that is, what is the effect of a solute on the freezing and the boiling points of a solvent? And to look at that, let's imagine what it means for vapor pressure to be lowered. That means at every temperature on the phase diagram, the vapor pressure of the substance is lower. So this is pressure on this axis, and this is temperature. I can take the boundary between the liquid and the gas, which is really what the vapor pressure is, and I can shift it down. The whole vapor pressure curve is shifted down a bit because of Raoult's law. So what effect does that have on the freezing point? Well, now the liquid-solid gas interface, the triple point, has been shifted down because that's where the liquid vapor line meets the solid vapor line. So this is no longer our interface. It's been shifted down. Because of that, the solid liquid line has to move down as well. So if normal freezing point is 1 atmosphere of pressure at the solid liquid interface, what's happened is we've taken our freezing point, which used to be here, and we've moved it down to here. So there's a freezing point depression. The freezing point of the substance goes down. And we call that freezing point depression delta TF. It's freezing point depression. It turns out to be directly proportional to the concentration in molality. And so we have a law. Freezing point depression says delta TF, freezing point depression, is equal to KF, that's a constant number, it's just the constant of proportionality, the slope of the line, times the molality of the substance that's dissolved in it. Now let's look at what happens to boiling point. Here's the normal boiling point, right here. That's where the 1 atmosphere line interfaces with the old liquid vapor line. But now the liquid vapor line has moved, and so we see a new boiling point up here. And so we now have an increase in that phase change temperature. And this is called delta TB, or boiling point elevation. So the boiling point of a solution is higher than the pure solvent. And again, it turns out to be directly proportional to the molality. So we have another law about boiling point elevation. Delta TB is equal to KB times molality. And KB is just a constant that's going to depend on the solvent. And you can look it up if you need it. And the same thing is true for the KF that we saw before. Both of these depend only on the solvent, and you can find them in reference materials or on the internet. So just to review, the freezing point of a solution is lower than that of the pure solvent. And how much lower it is called the freezing point depression, delta TF, and that's equal to a constant number that you can look up times molality. If the boiling point of a solution is higher than that of the pure solvent, and the amount that that boiling point gets increased, the boiling point elevation, delta TB, is equal to KB times molality. So here's a problem that allows us to work with this freezing point depression. It says, estimate the freezing point of an antifreeze solution made from 100 grams of ethylene glycol, which is C2H6O2, and 100 grams of water. And Kf for water, which we're considering the solvent here, is 1.86 degrees C per molal. Well, we know that freezing point depression is equal to Kf times the molality. And we know what Kf is that's given to us. So we have to figure out the molality of this solution. Molality, recall, is number of moles of solute, which in this case is C2H6O2, divided by the kilograms of solvent, which in this case is water. Well, how many moles of solute do we have? We know we have 100 grams of our solute, and it's C2H6O2. The molar mass of C2H6O2 is 62.068 grams per mole. So that means we have 1.611 moles of solute. So the molality is 1.611 moles of solute divided by 100 grams in kilograms. Well, if you divide by 1,000, you find out that that's 0.1000 kilograms of water. So our molality, when you do this arithmetic, is 16.11 molal. So what's our freezing point depression? Delta TF is equal to 1.86 degrees C for every molal of concentration times the 16.11 molal concentration that we have here. Molality drops out of here, and we get our freezing point depression in degrees C, and it's 30.0 degrees C. Well, this is water, which normally freezes at 0 degrees C. If we subtract 30 degrees C from that, we find out that this solution will now freeze at 30 below 0. This is why we put antifreeze in our car. Water would normally freeze at 0 degrees C and become a solid. This allows us to have our car out in temperatures as low as 30 degrees C without the coolant in our cars freezing. This is also why we put salt on the roads. When we dissolve salt in the water that's falling on the ground, it keeps it from freezing down to a certain point, lowers the freezing point, and that keeps it liquid on the road, which is, of course, a lot safer to drive on than ice.
For the last time, I'm pretty sure what's killing the crops is this Brondo stuff.
The Brondo's got what plants crave. It's got electrolytes.
So wait a minute. What you're saying is that you want us to put water on the crops?
Yes.
Water? Like out the toilet?
Well, I mean, it doesn't have to be out of the toilet, but yeah, that's the idea.
But Brondo's got what plants crave.
It's got electrolytes.
Okay, look. The plants aren't growing, so I'm pretty sure that the Brondo's not working. Now, I'm no botanist, but I do know that if you put water on plants, they grow.
Oh, well, I've never seen no plants grow out of no toilet.
Yeah, that's good. You sure you ain't the smartest guy in the world?
Yeah.
Okay, look, you want to solve this problem, I want to get my part in, so why don't we just try it, okay? And not worry about what plants crave.
Brondo's got what plants crave.
Yeah, it's got electrolytes.
What are electrolytes? Do you even know?
It's what they use to make Brondo.
Yeah, but why do they use them to make Brondo?
Because Brondo's got electrolytes.
Well, let's answer the question, what are electrolytes, so that we do know what they are. When ionic solids dissolve in water or another polar solvent, the ions are going to dissociate, and that makes something an electrolyte. Let's look at sodium chloride as an example. If you put sodium chloride crystals in water, they dissociate from each other and give you sodium ions and chloride ions. The same thing is true for ammonium sulfate, which is just another example of an ionic solid. And it's going to give you NH4. It's going to give you two of them, actually. And it's going to give you S-sulfate, SO4 2-. So now you have more particles in solution than the original concentration would seem to indicate, because they split up. A consequence of this is solutions like this conduct electricity. Strong acids will do this too. For example, if I have hydrochloric acid, this is hydrogen chloride gas dissolved in water, because it's such a strong acid, it's going to ionize and produce H pluses and Cl minuses. When you have charged particles that are free to move around in solution, you have something that conducts electricity, and that's what an electrolyte is. Electrolytes, it turns out, have an effect on colligative properties, and that's because colligative, remember, means depends on number, not on nature. It depends on the total particles that are in solution, not on what type they are. Best probably to learn this from example. So let's estimate the freezing point of aqueous 0.106 molal magnesium chloride. First of all, let's look at what happens when magnesium chloride dissolves in water. MgCl2 solid becomes Mg2 plus particles in aqueous solution and 2 Cl minus particles in aqueous solution. So every mole of magnesium chloride that we dissolve actually gives us 3 moles of particles. So if we have 0.106 molal MgCl2, what we really have is 3 times 0.106 molal particle concentration, and that's equal to 0.318. So our effective molality here really is 0.318 molal. So what's the freezing point depression? Well, delta TF is equal to 1.86 degrees C per molal times what we now know is an effective molality of 0.318 molal. When we multiply this together, we get 0.591 degrees C. So the freezing point is negative 0.591 degrees C. What would that freezing point have been if this weren't an electrolyte? Well, we can redo this calculation with the wrong number, which is 1.86 degrees C times 0.106 molal. The freezing point depression would only have been 0.197 degrees. So we see a substantially larger depression in the freezing point with an electrolyte than we do as a non-electrolyte. Now it turns out that splitting all the ions up just the way the stoichiometry shows isn't always exactly right. Some of the ions actually stay together as something called an ion pair, so almost like a molecule. So the actual particle concentration is often slightly less than you'd expect with 100% dissociation. We keep track of this with something called the Van 't Hoff factor. It's the ratio of the actual concentration to the concentration if the solute weren't an electrolyte at all. This was originally defined in terms of freezing point depression, and so I, which is the Van 't Hoff factor, is the ratio of the delta T you actually get, the measured delta T, freezing point depression, or boiling point elevation, divided by the delta T that you'd calculate if it weren't an electrolyte at all. But remember, delta T is equal to K, let's use freezing, Kf times molality. So the only thing that's different is the actual molality divided by the molality as a non-electrolyte, and Kf will be the same for the same solvent. So I is also a ratio of the actual molality, or the effective molality, to the molality if it weren't an electrolyte at all.